Okay, so this is the computation of the area. And one thing we were able to get around is carrying out the back substitution all the way back to x. So the original integral is right here at the top left. Okay, so it's with respect to x, and as you can see, we were able to use our knowledge of how to do substitution in definite integral to avoid doing that. And as you can see, the limits were taken care of here, and that's how we got the answer of pi over 2. So, but the integration techniques, which is what this chapter is about, is strictly speaking about finding antiderivatives, not about the limits, even though it is a nice shortcut. So we would like to be able to indeed carry out all the back substitution all the way backwards. So not staying here, as you can see, which is with respect to t, but rather just do reverse the substitution, which was x equal cosine t, and get to back to a function of x, which is antiderivative, cannot be in terms of some other variable. Even though certainly you can appreciate what has happened here, it is actually a big lesson about long-term use of what we did here. It is a change of variables. Okay, so changing of variables from x to some other variable that is convenient for one reason or another. Okay, so sometimes it's possible. So we ended up with sine of 2t, where t is cosine t. So in other words, we are facing this expression over here, sine of sine of our cosine. Sine over cosine, which is really not a very useful expression. So what is z equal sine of our cosine? So we can simplify it. It's supposed to be of x. So we still want it to be in terms of x, but with the knowledge of that x is cosine t. X is cosine t, the our original substitution, and so which means that we could build this little triangle. That's not a z, this is a t. Okay, we can build our little triangle here. That's the technique that we use to simplify things of this nature. Once again, a composition of two functions, one of which is trigonometric and the other one is an inverse trigonometric. So of course this one is easy to, well, how do we simplify this one?
It's just t.
They're just t. Okay, good. So when it is the same function in its inverse, we know that we can simply cancel them because they do cancel each other. Okay. When it is one sine and the other one is cosine, then they don't match, and we cannot just cancel it. But fortunately, this picture is quite revealing about what's happening. So x is equal to cosine t. T is the angle. As always, x is one of the sides. This is the side. Okay. Whenever the hypotenuse is 1, right? So x it is the adjacent side is the hypotenuse times the cosine of the adjacent angle, which is what I just written. Okay. So we know then the three parts of these triangles are known: t, x, and 1. And now we'll look at z, and we try to realize where that z is. And since x is cosine t, in the meantime, so it means that t is our cosine of x. Okay. Which means that in that expression of z, we have simply z is equal to sine t. Okay, so in other words, we break this composition into two and introduce an extra variable in the middle. Okay, so which is t. Okay, so in other words, we made all the way through this with the substitution. saw what we have at the top, realized that this is a very cumbersome expression, and tried to make a little step back to t in order to resolve it and put it in a more appropriate terms. And we almost have, because now z is equal to sine t, but we knew that. But the point being is now we still have to get to x. How? Well, where in this triangle is sine t? So where is it? Can you see it on the triangle? What?
The opposite of the
It is the opposite, the other side. So it's opposite of sine. So once again, this is my cosine. It's the adjacent side, okay, and this one is the opposite side here. Okay, so we know where our z is. Z is what we're after. So what just remains is we still have to express in terms of x. So we then throw out we'll try to throw out trigonometry, indeed. So we don't care about that anymore. Oops. So what's left is then once again 1 x z right angle t. Well, we don't need t anymore. Okay, so we don't care about t anymore. Okay, x, z, that's all there is. So this is the result. We have a right triangle with hypotenuse 1 and 2 of the sides equal to x and z. X is what we know, and we want to express z in terms of x, and that shouldn't be too complicated. So what is z in terms of x?
The square root of 1 minus x squared.
That's right. That's all. So we just use the Pythagorean theorem to eliminate this complexity. Okay, and so then no surprise. Then the result is we sort of back to something that looks very much like the original integral. Remember that in fact, this is what we tried to integrate to begin with. That is the equation of the circle radius 1. And then when we did we finished integration, indefinite integration, we ended up with a function that involves this. Okay, so there you go. We have, not surprisingly, we have once again something that is something about circles again. So we'll do this one more time with the next integral. Also, the same trick. The same trick is to find an appropriate triangle and combine your knowledge of trigonometry, right? So that's what we did. We used what we know about cosine and about sine, and then finally using the Pythagorean theorem, which makes everything, which eliminates trigonometry. Okay. It is kind of surprising. So compare. That's kind of an accomplishment that we have, the original, and this is what we ended up with. So trigonometry, even though it did not cancel itself as easily as on right over there, but it still simplified things so significantly that the function is actually quite simple. Okay, so in fact, if you think about it, what we end up with is a function that well, let me show you where we came from. Here. Nope. Yeah, so there are two terms, as you can see. This is what we're talking about. We have been taking care of the second term, which ended up to be a rational number, or rather algebraic expression. Okay, but this will still be arcsine. T certainly is arcsine, so it is inevitable. I'm sorry, arccosine of x. Yeah. Okay. So and that way we can actually write out the formula. Okay, so let's do the fix that problem, that integral that I got stuck with. Well, it turns out this is just not what I had in mind. I want to do instead the reciprocal of this, which turns out to be slightly easier. But also we have to go through all the steps. It is easy, but not really that easy. So what I want to do is 1 over 1 plus x squared. or x squared plus 1. Square root. Okay, so once again, cheat sheet suggests that the substitution, it should be x equal tangent t, right? Because once again, where's that list over here at the top? So this is where we are. So tangent is the substitution. So then tangent is a little more complicated than cosine. So it's sine over cosine. So the derivative is complicated, and the as well as the derivative of the derivative. Okay, so x is tangent x. Dx, this part we already did, so it is secant squared t dt. Okay, so and then thirdly there is let's look ahead and just figure out what x squared plus 1 is. We also did that yesterday. So it is we used the formula from trigonometry, which gave us secant. Right? So that's the idea of a simplification. So now if we finally take these three, well, in fact, the last two only matter. So this is the substitution. Should choose the new variable t is expressed in terms of the old variable. Then we produce from that we produce this. And then these two combine together, dx, as well as the expression for the denominator, gives me a new expression for my integral, and instantly entirely in terms of t. So secant t, and this is secant squared t dt. Okay. Did you follow what I did?
Where does the x squared plus 1 equals secant t? Where does that come from?
We talked about that yesterday. Remember, secant squared plus what is it? Secant squared minus tangent squared. Remember?
Yeah.
So I guess I just skipped it. Let me write it out. So tangent squared t plus 1 is equal to secant squared t. Okay, so that's a trig formula that we use here. Okay. Okay, so things simplify slightly. We end up with integral of secant t c dt. So if it is done previously, and sometimes you can start with these integral to figure out what secant is to begin with, or you can look it up in the just like every integral, you can look up in the list of integrals. But since we didn't do this before, then let's just carry out this integration, and the integration is complicated. So and once again, it's almost like by magic. We choose a new variable, secant t plus tangent t. It looks funny because why would anybody would come up with this idea to carry out this substitution when the integral looks fairly simple to begin with, and then the answer is somebody tried and finally came up with this idea. Okay, but there is no other explanation, and and even then it was not instant, as you can see. So whenever you try and fail, it is something to be expected when you do integration. Okay, so the du then, just like before, is just remembering. Let me just write the formulas that I have here. Well, certainly the last part is familiar. The last part is familiar. So the derivative of tangent is secant squared. Right? Yeah, okay. And secant squared, well, If you haven't carried out the computation, certainly not unlike integration, it's very easy to differentiate. So secant is simply 1 over cosine. So well, there you go. Secant t is 1 over cosine t, and so if you integrate and you apply to differentiate, what do you do? You do use the quotient rule, right? And so it will be what is it? It's going to be negative sine over cosine squared, right? Okay, and that, well, another way to express it is to write it as secant times t. Okay, so it's kind of complicated, but surprisingly it works out. Not easily, but so I put secant here, and I put the my derivative of the derivative that the expression in the parentheses at the bottom. I put it here, plus secant squared. Okay, secant t times tangent t plus secant squared t. Okay, so that's the same. This is simply 1, right? Remember this trick that we use sometimes. And then I already know. Then look at it. I can now see that I have my du already here. So that by design, this is by design. So once we know what the substitution is, we know what to look for. So this is du. Hold on a second. Yes, it is. Yeah, this is du. Okay, so what remains is to see where my u is. Okay, so now let's look at what's left. This is what's left. It is a complicated expression, but what's supposed to happen is express it in terms of u. Well, let me erase this for the time being. So there is some algebra here. So what is it, that expression? It's secant divided by secant t divided by secant t times tangent t plus secant squared t. And I will certainly I'm not in the position to divide, but if I take the reciprocal, I could reciprocal of the reciprocal. Okay, so I flip my fraction here. So secant t times tangent t plus secant squared t divided by secant t, right? So what do we have here then? Okay, so 1 over and tangent t plus secant t. Okay. So what are we looking at? It is 1 over u. That's right. So we'll look at u. So that was certainly by design. So was it clear how I simplified the last line? So secant t times tangent divided by secant. I split the numerator, and so I divided secant times tangent by secant. I ended up with tangent. That's the first term, and then the secant squared divided by secant is give me secant, right? So secant disappears here, and secant squared disappears there. Squared disappears, right? Okay. So and then this is simply u. Just let me circle it for you here. So this is secant plus tangent right here. So it is indeed 1 over u. Okay. So so then what's in I've got in my integral is 1 over u du. Right, so this is the yellow part that we have simplified so significantly, and then the green part right here, it is du that we already had some time ago. So as you can see, the integral becomes very, very simple. How you discover that, once again, I cannot tell you. Okay, but this we can now finish it. So what's the integral 1 over u? Integral of 1 over u. What? Natural log of u, more precisely, absolute value of u plus c. Back substitution, plugging everything back in. So it will be tangent t plus secant t, absolute value plus c. Okay, and now we are approaching that uncomfortable place again, where we're going to have a composition of a trig function and its and the inverse of another trigonometric function. Okay, so because remember what t is, we're done with all these complexity, but there was the first substitution that we carried out is right here. X is tangent t. Okay, so certainly if we are going backwards, this one is easy. This one is x. This is x. But what about secant? Okay, so in other words, I'm not going to write this. I don't want to substitute t, even though we know that t is equal to once again our tangent of x. Okay, so I don't want to do that substitution because it's unacceptably complicated, especially we already know how to simplify. So the plan then is express secant t in terms of secant t in terms of x, which is tangent t. Okay, so there are two expressions. Well, once again, let me put z here. Two expressions, both are trigonometric functions of the same variable t, and now we want to express one in terms of the other. Okay, so how do we do it? Once again, we got to have a little triangle with t. Well, you can guess that it's going to be an angle in that triangle. Okay, a right triangle. Okay, so this is t. Let's find x and z. So can you find x? Well, x is, as you know, sine t over cosine t. It is what? No. No.
X will be the opposite side of the angle.
X will be the opposite whenever. So this is x. This is x under an extra condition. X is here. Sine over cosine, whenever it is the x, if you just look at this, what this is, it is in fact the it is the sine of t if the right. No, that should be equal to 1. The other side, this is cosine. This should be 1. Does it make sense? So the tangent is in fact the ratio of the opposite over the adjacent. Right? So x is tangent, so well, there you go. So this is x over 1, and so x is opposite, and 1 is adjacent. So it is up to me to choose the side of the triangle. I choose it to be equal to 1. Adjacent. Okay? So I choose it equal to 1, then everything works out. So I'm not worried about z just yet. I'm just trying to find x here, and I have right here. It is the side opposite to t whenever the other side, not the hypotenuse, as last time we did with the hypotenuse equal to 1. It was simpler. This one is slightly more complicated, so I choose the other side to be equal to 1. Okay, so then I have my triangle ready. So it's fully determined because there's an angle and the two sides have been given. And now I need to find what I'm after, and that is, what is it? Secant t. secant t. So where is secant t? So now find z equal to secant t, which is also 1 over cosine t. Except, once again, I don't want to do any trigonometry. I want to use the Pythagorean theorem, right? So I could just go on and let me once again use the idea of trigonometry as it originally put forward as opposite over adjacent or something like that. So let's take cosine and let's express it once again in those terms. So cosine in any triangle is what? It is adjacent over hypotenuse, yes. Over hypotenuse. So since it's reciprocal, we end up with hypotenuse over adjacent. Okay? The adjacent is what? No, 1. 1, right? And in the hypotenuse?
The square root of x squared.
Yeah, that's right. X squared plus 1 squared. Okay, so that does it. So we have found indeed that secant in a very nice as a very nice expression. So once again, this is z x squared over square root of x squared plus 1, and we just plug it in back into my my equation. So I continue on. Question? Okay, so what do I have here? Natural log. Tangent t is simply x, and here I have x squared plus 1 squared. Okay? So it is all possible. It is such a multi-step procedure. You in calculus 1 probably the substitution were shorter. Didn't take as many steps, and that nice trick at the end also not very easy to come up with of how to simplify such complicated trig expressions. But as you can see, it is about a page of computations. There is no way that second substitution can be. The first substitution would have a cheat sheet, okay, so we can always look it up. But the second one is more complicated. It's almost a miracle. So I don't want to allow you to see trig substitution as separate from the rest of the substitution. It's still substitution. You still go through the same steps. You express the new variable in terms of old, or vice versa. You also deal with the dx and dt, okay, whatever your letter is, and then you carry out the substitution in a complete manner. So there are no over here, as you can see, that's the substitution is finished here. It is when all the x's have gone. But not by accident, but it was very carefully substituted. Dx was substituted. See, this is dx, and it was replaced with this expression, and then this expression was also found through the choice of x, choice of t rather, and some trigonometric formula. And then ultimately it simplifies a little bit better. But actually, this is the end of substitution. So you have two integrals side by side, or one under the other, and they are we change variables. It is substitution sometimes is a bit of informal language, or it does not reveal how much actually is behind this, and what is behind it is change of variables. So one variable with respect to one variable becomes an integral with respect to another variable. Okay, and that's the essence of substitution. Why it is substitution? Because remember where it comes from. It comes from compositions. So you evaluate compositions by you have several functions, and you substitute function into the next function. So the output of the first function substitute into the second, and the second into the third, and so on. So that's the substitution part. But it's really about compositions, and in the end of that chain of events, you end up with an entirely new function or integral with respect to a new variable. Okay, this one, once again, don't forget that behind not this, but the previous example, we we are talking about t as the angle or t as the time, if you prefer to think about motion. So angle or time. Okay, so there will be a few examples, not of this complexity, but it's comparable as far as tests are concerned. Then such a problem will be probably split into different pieces, so that you don't have to do all the whole thing, because one little mistake and then you pretty much stuck. So that's what to expect. And meanwhile, we'll just move on to the next topic. Still integration, but this one is different. So this one is called integration by parts. So beyond the review, this is only our second topic. So the first one was trig substitution. The second one is now integration by parts. But first let me make it clear that integration is the reverse or inverse reverse. It's certainly informal somewhat of differentiation. And as such, and then integration by substitution comes from what? So the formula of integration by substitution comes from a certain formula about differentiation. What is it? Okay, let me give you an example, which repeated many times. So u is x squared, and this is it will be what? EU du. Okay, so that's an example of integration by substitution, right? And do you see a formula from about differentiation that is being used here? Okay, let me make one more step here. Ex squared prime is equal to what? 2x e to the x squared. So that is the left hand side of the integral right here. Right. So this is what we're integrating is in fact the output of differentiation. We try to reverse this differentiation. So this one is easy. Once again, calculus 1, differentiation, and we're trying to reverse it. We're trying to recognize the answer to some question that we don't know what it is. Okay, so the result of differentiation is what we're trying to identify here. And in this particular case, and we did, sometimes it's fairly straightforward, but only after you've done a lot of differentiation to begin with. So if you've done something like that many times, you might simply look at that integral on the left and say, well, that's the answer. Okay? If not, then you carry out the substitution, but you still have to figure out what your substitution is, and that might be tricky. But certainly, it works out most of the time. So this is, if you choose this u, then that's your substitution. Okay, so let's say, how do we end this sentence on the right? Integration by substitution comes from, specifically, what is that we use there at the bottom? How did we differentiate the function at the bottom? The chain rule. So it comes from the chain rule. In a sense, it is the chain rule. It is the chain rule combined with what? With understanding of the integral as the inverse of differentiation. With that understanding, where does it come from? It comes from the fundamental theorem of calculus, right? So that's how not everything, but a lot of things that we can do about integration comes from differentiation, and sometimes it becomes as complicated as you can see here. So that was, I mean, if you've done enough differentiation with the chain rule, that would, at the bottom is very easy. Okay, and somebody was able to give the answer very quickly because you've had enough experience with that. But integration, just reversing that the direction, it becomes complicated. In fact, not just complicated, you might fail to begin with. You never fail with differentiation. Okay, so that's the lesson. But then if the integration by substitution comes from the chain rule, one of the rules of differentiation, then what about other rules of differentiation? And one of the rules of the differentiation you have already seen. Those are the sum rule and the constant multiple rule. Okay, so sum rule of differentiation produces the sum rule of integration, right? So it's certainly helpful, and we have been using it very casually. So say f plus g dx is equal to integral f dx plus integral g dx, and then similarly, in addition to the sum rule, is the constant multiple rule. Right. So once again, you certainly remember the sum rule, the constant multiple rule for differentiation, and these are their counterparts for integration. So as you can see, we have 3 rules already that have counterparts. 3 rules of differentiation that have counterparts for differentiation, for integration. Okay. And there are what other rules do you remember? Rules of differentiation. They usually go in that order: sum rule, constant multiple rule, something, and then the chain rule. What? The product rule, right. So the product rule is, let me write it out, the product rule for you. Product rule of differentiation first, because once again, it's not going to be as easy as these two, and it might be as complicated as that one. Okay, so the product rule is complicated, and because it gives you a combination of functions and their derivatives. Okay, so that's the product rule. Once again, assuming all differentiation, all the caveats apply, and then we will try to reverse, using the fundamental theorem of calculus, reverse this operation in order to somehow use it to integrate. Okay. So let's not make it more complicated than it has to be. So let's just integrate. So integrate this. Integrate both sides of the equation. After all, what are these if not two functions? I have a function on the left, I have a function on the right. They are equal to each other, which means that their integrals will be also equal to each other. Right? Okay, let's simplify. Okay, what can we do on the left? What can we do on the left? What?
Would you cancel out the integral?
And the derivative, yeah, based on what? How do I justify this? Cancellation.
Because integration is just the reverse.
Yeah, well, right, yeah. What I meant is we're trying to justify everything with referring to a theorem. In this particular case, I'm talking about the fundamental theorem of calculus. Indeed, it is fundamental, so that's why. So you can certainly, whenever if it's a test and you need to justify something, you certainly can justify it as just saying what it is, or you can just name names. You say what it is, name the theorem you're referring to, and that is sometimes easier. But it's up to you. So by the fundamental theorem of calculus, these two cancel each other up to a constant. So be careful about that. The cancellation. So technically, I would have to write plus c here. We just I can drop it as will be clear in a minute. On right, I have two integrals: f prime g dx plus f g prime dx. Okay, so it does not look like a formula we can use for integration. So it does not look like any of these on the right, or even the integration by substitution formula. Okay, so what to do? It turns out we just rearrange the terms, and to make it useful, we'll try to do. How about this is known, and this is known, and then we'll say, well, how about this is unknown? I think I picked the right one. G prime. Let's do the other way around. So these two are known. And this one is unknown. So in other words, it's just a matter of solving equations. So I have integral f times g prime dx is equal to f times g minus integral f prime g dx. As you can see, what happens here is if on the left-hand side the f is present and the derivative of g is present. Okay, on the right is the opposite. So the derivative of f actually appears and the derivative of g disappears. Okay, so it might be unclear why it is helpful. But let's first, before we do that, let's recognize that the presence of the derivatives actually allows us to simplify things quite a bit and make the formulas slightly more manageable. So if we take a careful look at these two expressions, remember what they are? No, the one is, they are the same, but one is about g, the other one is about f. Remember we just did it today a few times, yesterday. Derivative times dx, what is it?
It's the original function.
It is dg. This is dg, and this is df, right? Okay, so that makes a slightly more compact formula, and ultimately more usable formula. So integral f dg equal f g minus integral g df. So it's another formula, and another form of the same formula comes directly from the product rule. In fact, you can actually go backwards and recover the product rule from this using the fundamental theorem again. But how can we use this? How can we use it? And the example is this, an example of how this works out. Let me just do one. Okay, here's one. Integral x ex. If you look at a minute ago, here's the example, almost identical formula, except we have x squared in the numerator. I'm sorry, in the exponent we have x squared, which makes things complicated. But on the other hand, we know that we can solve it. We can solve at the top by substitution. However, here we have no chance of that substitution to be working because there is no x squared. We do see a multiplication here, but there is really no substitution or something, anything that would suggest that I should try substitution here. Fortunately, this formula called formula integration by parts why by parts we'll just see in a minute. If we look at this formula, either one of these two formulas is equally good for us to approach. And in fact, the first formula might be slightly easier. What I'm supposed to do is to match the left-hand sides of these two equations. So I'm going to match these. Okay, so well, you can see that if I try to match them term by term, it appears that f of x is equal to x, and g prime is equal to e to the x, right? Let's see what happens. So there is nothing, if we're gonna apply our formula that, as you can see in the right-hand side, we're gonna need the derivative of f, so let me just right away compute f prime, which is 1. And then we compute in g. How do we compute g here? We compute it by integration, and that is the first part of integration. There will be two integrations, and this is number 1. So to find g, how do I find g from its derivative? By integration. So I am integrating e to the x dx, and the answer is naturally e to the x plus c. Okay, so things seem to be working out, and now let's use the formula. So use the integration by parts formula. It's right at the top, so I'm just copying. I know what my f and g are. Okay, so what if I continue writing here? So this is equal to. So we did the preliminary work here. Okay, so what I am producing here is fg. I am going diagonally. F is x, g is e to the x. Okay, that's the first term. And then I have that second integral. So one integral turns into two, but things do simplify. Why? Because look at what's f prime. F prime. It's simply 1. So that over there at the very top, it starts with nothing but 1, and then it's followed by g, which is e to the x dx. And this is certainly manageable. So we end up with x e to the x minus e to the x plus c, and that's it. So it really worked out very nicely. So then we have now two main rules of integration, and we have to figure out which one to apply whenever you encounter an integral. Okay, so we'll just continue this next week.